Hello, I'm Masashi Watanabe of University of Southampton. In this time, I would like to explain about sediment transport by a tsunami for prediction of coastal process based on numerical modeling. Predicting coastal geomorphological change is very important for coastal preservation and maintenance of the coastal environment. Because coastal regions has rich ecosystem and coastal regions has been used as the center of economic activities and industrial activities for us. Sometimes by a tsunami, severe coastal erosion is happened. For example, this picture shows coastal erosions induced by a tsunami at muddy coast and sandy coast. The coasts are composed of boulder, gravel, sand, and mud sediments. So, in order to understand coastal geomorphological change by a tsunami, a sediment transport induced by a tsunami need to be predicted. For the construction of parallel tsunami from tsunami deposits, the numerical modeling of sediment transport by a tsunami is also important. Maybe as you know, tsunami deposits are defined as boulder, gravel, sand, or mud sediments deposited by parallel tsunami. In 2019, I investigated all tsunami deposit data so far. As a result, 46% of reported tsunami deposit was sand sediments, and 70%, 24%, and 30% of reported tsunami deposits were mud sediments, boulder, and gravel sediments. By investigating the size of parallel tsunami, which can explain the distribution of onshore or offshore tsunami deposit based on numerical modeling, the specific size or specific location of parallel tsunami can be investigated. For this, numerical modeling is a strong tool. So far, for the modeling of tsunami wave or modeling of sediment transport induced by a tsunami, two types of numerical modeling have been used. One is grid system and another one is particle system. In the case of grid system, at first you need to decide on computational domain. Inside of the computational domain, you need to set computational grids. So, fluid out of the numerical domain cannot be calculated, and fluid movement is basically along the grid shape. Therefore, when you used the grid system, the determination of computational numerical domain and grid cell size are very important. And it is also difficult to calculate wave splash like wave breaking in the case of grid system. When you want to reproduce wave breaking reasonably using grid system, you need to set fine grid cell at the site where wave breaking is generated. In the case of particle system, numerical domain don't have to be set, and it is easy to calculate wave splash like wave breaking, but this computational load is very high compared to the grid system. So these are the simulation movies of double leg flow using grid system and particle system. In the case of grid system, I used CAD/Math 3D. CAD/Math 3D is the open source model which can solve Navier-Stokes equation directly. In the case of particle system, I used Dual's physics. Dual's physics is also the open source code based on SPH method. So like these simulation movies, another advantage of particle system is that you can make beautiful movie, but the computational load of SPH method is very high, as I explained. Next, I would like to explain about unique characteristic of boulder, gravel, sand, mud sediment transport by a tsunami. In the case of mud sediment, considering cohesiveness of mud sediment is important for the simulation, because mud sediment is classified as a sediment that its grain size is less than 1/60 mm. So the grain size of mud sediment is tiny, so each mud sediment particle is connected to each other by their van der Waals force. So during a current and waves, mud sediment are transported as a flock because mud sediments are connected to each other chemically during current and waves. and the formation of frog in the water depends on water temperature, salinity in the water, or current velocity or wave velocity. So this effect need to be incorporated in the simulation. And basically, mud sediments are transported as suspended load by a tsunami. In the case of sand sediment transport by a tsunami, a sand sediment is called as non-cohesive sediment because the found mass force between a sand particle and sand particle is relatively small compared to a mud sediment, and this effect can be ignored. And basically, by a tsunami, sand sediments are transported as petrol and suspended loads. So when you simulate sand sediment transport by a tsunami, both petrol and suspended load need to be predicted. So another unique difference of mud and sand sediment transport by a tsunami is particle density stratifications. So this picture shows laboratory experimental results of sand and mud sediment transport by downwake flow. In the case of sand sediment transport, the sand sediment were transported near the bed, and the density of suspended sand sediment near the bed is significantly higher than the density of suspended sand sediments near the water surface. In the case of mud sediments are distributed uniformly in the vertical direction, and the density of suspended mud sediment near the bed is almost same with the density of the suspended mud sediment near the water surface. And this is the numerical simulation results of sand and mud sediment transport by a tsunami using Delft 3D. For these simulations, I set 10 vertical layers, so vertical movement of sand and mud sediment could be simulated in these simulations. So in the case of mud sediments were transported near the bed as well as the laboratory experimental results, and in the case of mud sediments were distributed uniformly in the vertical direction. And this is a simulated thickness of onshore sand and mud sediments. In the case of sand sediments, when density stratification were not calculated, the simulated thickness of onshore sandy deposit were overestimated. When density stratification was calculated, the simulated sand thickness were consistent with observation results. In the case of mud sediments, even if density stratification was calculated and was not calculated, the simulation results were almost same, and simulated onshore thickness of mud deposit were consistent with observation results. Therefore, when you calculate sand sediment transport by a tsunami, the calculation of particle density stratification is very important. These are the examples of sand and mud sediment transport by the 2011 Tohoku tsunami at Sendai Plain, Japan. In the case of sand sediment transport, erosion and sedimentation of sand sediments were almost finished only by the first wave. In the case of mud sediment transport, it took 3 or 4 hours to finish the erosion and sedimentation of the mud sediments. So, when you predict mud sediment transport by a tsunami, you need to set longer simulation time. So next, I would like to explain about gravel sediment transport by current and waves. So far, numerical modelings of gravel sediment transport by storm waves have been conducted. For example, MC Cole et al. 2012 and Jamal et al. 2014 conducted the numerical modeling of gravel sediment transport by storm waves. Right figure shows the simulation results of erosion and sedimentation at gravel beach induced by storm waves when the calculation of groundwater flow was not included and the calculation of groundwater flow was included. When the calculation of groundwater flow was included, final distribution of erosion and sedimentation at gravel beach were consistent with observation results. But when the groundwater flow was not calculated, especially the intensity of backwash due to storm waves was not reproduced. So the final distribution of erosion and sedimentation at gravel beach were not consistent with observation results. So when you predict gravel sediment transport by storm waves, the calculation of groundwater flow is important. But the effect of groundwater flow in the case of gravel sediment transport by a tsunami has not investigated so far. So this effect needs to be investigated in the future. Next, I would like to explain about border transport by current and waves. When you predict border transport by a tsunami, the prediction of border transport mode is important. For example, when border density is low and border velocity is high, border is transported as loading or saltation, meaning that friction force acting on the border surface is low. But when border density is high and border velocity is low, border is transported as sliding, meaning that friction force acting on the border is high. So if border shape close to cube shape, border density is low and border velocity is high, border transport mode is changed from sliding to loading or saltation, meaning that friction force acting on the border surface decrease. So right figure shows the simulation results and observation results of border transport. If constant roughness was used in the simulation, meaning that even if border transport mode is changed from sliding to loading or saltation, friction force acting on the border surface is not changed. In this case, the simulated border velocity and simulated border position were not consistent with observation result. And if empirical roughness coefficient, which can explain reduction of friction force acting on the border surface if border transport mode was changed, the simulated border velocity and border position were consistent with observation results. So from this result, for the simulation of border transport by a tsunami, the prediction of border transport mode is very important. Sometimes a border is transported onto the top of the cliff by extreme current and waves. For example, this is the 6,000 ton of boulders deposited on 12.5 meter cliff in Japan. It has been considered that this boulder was transported onto the top of the cliff by paleo tsunami. And this picture shows rectangular boulder and rounded boulders deposited on 5 meter cliff at Hachijo Island in Japan. In the case of rounded boulder, this boulder was in the water for a long time. Then this boulder surface was eroded by water current. Then this boulder's water surface was smooth. After that, this boulder was transported onto the top of the cliff. So this rounded boulder was transported onto the top of the cliff from under the cliff, and this rectangular boulder was transported from cliff edge. So these are the laboratory experimental results of boulder transport onto the top of the cliff. When wave hit to the vertical cliff, wave can move toward vertical direction. Then vertical wave force can act on the boulder surface. Then boulder was transported from cliff edge or from the under the cliff. So this is a simulation movie of boulder transport onto the top of the cliff by tsunami and storm waves. So in the case of storm waves, storm wave can transport boulder toward vertical direction. Tsunami as well. Tsunami, that wave period is short, like 5 minutes. Tsunami also can transport boulder toward vertical direction. But if tsunami wave period is long, like 12 minutes, a vertical movement of boulder was not occurred. Therefore, storm waves or tsunami whose wave period is short can transport boulder toward vertical direction. Then this wave can transport a boulder onto the top of the cliff. In this presentation, I explained about numerical modelings of coastal process induced by a tsunami. These modelings can be conducted using the following open source softwares. If you go to these URLs, you can download these open source codes for free, and in the same time, you also can download user manuals for free. By reading the user manuals, you can understand how to compile the open source codes, how to make an input file, how to run the software, and how to visualize the simulation results. So the use of this open source software is useful for understanding coastal process induced by a tsunami. So this is the end of today's presentation. To summarize, numerical modeling is an important tool for investigating coastal geomorphological change, but the accuracy of numerical simulation results need to be validated through fieldwork or laboratory experimental results. And each sediment, mud, sand, gravel, and boulder has a different property. So the appropriate simulation method needs to be chosen when you predict coastal geomorphological change induced by a tsunami. Thank you.